Thank you, JJ, for the information on the historical, social, and financial aspects of solar thermal systems. I'm Marcus, and I will go through the overview of solar thermal systems and the different types of solar collectors. But first, please watch this short video on the application of a solar thermal heating system. The video shown in the previous slide talks about a typical solar thermal system that can be used for household heating. A solar thermal system can be broken down into several parts. The key working principle of solar thermal systems is the absorption of solar radiation through the use of solar thermal collectors. These collectors are classified into two categories, non-concentrating and concentrating. A non-concentrating solar collector is generally used for low temperature applications such as space and water heating. Meanwhile, concentrating solar collectors are used in high temperature applications such as concentrated solar power plants, which focus the solar thermal energy onto a receiver. The heat is then transferred to a heat transfer fluid and retained in a thermal storage device. The thermal energy can then be used in the production of electricity through a turbine and generator. There are 6 types of solar thermal collectors falling in the low, medium, and high temperature range, which can be broken down into the two categories mentioned earlier. Flat plate collectors and evacuated tube collectors are non-concentrating collectors which do not concentrate solar radiation. The remaining 4 are compound parabolic concentrator, parabolic trowel collector, parabolic dish reflector, and linear Fresnel reflector. They are concentrating collectors that concentrate solar radiation onto a smaller receiving area by using reflective surfaces to increase the radiation flux. The two types of non-concentrating collectors differ slightly in terms of their working mechanism. Flat plate collectors, or FPCs, are metal boxes that have a transparent cover over an area with a black absorber plate. Solar radiation passes through the transparent material and is intercepted by the absorber plate. This heats the plate up and transfers the heat to the fluid in the FPC. These absorber plates are usually made out of a metal that is a good conductor. They are painted with special coatings to increase absorption and the retention of heat. The sides and bottom of the collectors are also lined with a layer of insulation to reduce heat losses. FPCs use both direct and diffuse solar radiation. They are designed to operate at a maximum efficiency in the low temperature range of less than 100 degrees Celsius. Major applications of these units are in solar water heating, building heating, and air conditioning. Evacuated tube collectors, or ETCs, consist of single tubes that are connected to a header pipe. These collectors are characterized by a heating pipe placed inside a vacuum-sealed tube to reduce heat losses of the liquid to ambient air. The heat pipe contains a small amount of liquid that undergoes an evaporating and condensing cycle. In this cycle, solar heat evaporates the liquid, and the vapor travels to the heat sink region where it transfers its thermal energy to the heat transfer fluid and condenses in the process. The condensed fluid then returns back to the bottom of the tube, and the process is repeated. The heat pipes are generally treated with a dark-colored paint to better absorb solar radiation. The combined effects of black coating and vacuum insulation of the absorber provides ETCs to have high heat extraction efficiency when compared to FPCs. The ETCs are often used in low temperature applications ranging from 60 degrees Celsius to 80 degrees Celsius. Note that an ETC must always be mounted at an angle in order to allow the condensed internal fluid of the heat pipe to return to the bottom. Concentrating collectors use an optical system that directs solar energy onto the receiver. Concentration can be obtained by reflection or refraction of solar radiation through mirrors or lenses. These concentrating collectors provide energy at higher temperatures than that of FPCs and ETCs. However, they usually require tracking of the sun. These collectors move throughout the day to maintain a high degree of solar radiation concentration on the receiver. Solar thermal power plants utilizes concentrating solar collector systems because they can produce high temperature heat needed to generate electricity. These collectors can also be classified into non-imaging and imaging, depending on whether the image of the sun is focused at the receiver. The concentrator belonging in the non-imaging category is the compound parabolic collector, or CPC, whereas all the other types of concentrators belong to the imaging type. CPCs have the capability of reflecting to the absorber all of the incident radiation within wide limits, either beamed or diffuse, intercepted over a wide range of incident angles. Therefore, such a system does not require tracking of the sun, resulting in a less precise but more flexible use. Despite the low concentration ratios, CPCs can be very useful for increasing the performance of systems at relatively low cost. In particular, regions where solar resource is less than ideal, such as most of Europe and some parts of USA. A parabolic trough collector, or PTC, is a linear focus solar collector. It is basically composed of a parabolic trough-shaped concentrator that reflects direct solar radiation onto a receiver tube located in the focal line of the parabola. The large collector's aperture area concentrates reflected solar radiation onto a smaller surface of the receiver tube, heating the fluid that circulates through it. Typically, rows of parabolic mirrors are mounted in parallel on either a north-south or east-west axis depending on the location and energy production requirements, and they move throughout the day to track the sun across the sky. Parabolic trough technology is the most common in solar thermal plants as the potential of these systems are high and can provide high output fluid temperatures in the range of up to 500 degrees Celsius. A parabolic dish reflector, or PDR, concentrates light in a single focal point. All sun rays that are parallel to the axis of the parabola are directed towards the central receiver. This allows the collector to achieve the highest concentration ratio amongst all the other types of solar collectors. The system must be orientated towards the sun, and it is achieved using dual-axis tracking. Usually, losses in this technology are associated with the imperfections of dish alignment and the non-ideality of reflection. This technology can be used for both large-scale power plants, with many dishes grouped in an array, or autonomous small-scale power generation systems. A linear Fresnel reflector, or LFR, is another type of solar power collector. It is a simplified parabolic trough which uses flat mirrors as opposed to parabolic mirrors. The basic principle remains the same, the mirrors concentrating solar power onto a receiver tube. An LFR works by utilizing the Fresnel lens effect. This design allows the construction of large aperture and short focal length lenses without the mass and volume of material that would be required by a conventional lens. It helps in the cost reduction as parabolic reflectors are costly to manufacture. However, one big disadvantage with this design is the shading effect of adjacent mirrors at low incident angles. To summarize, these concentrating collectors use reflective surfaces to concentrate light onto a receiver. The surfaces are either flat or parabolic depending on their type. These concentrators can increase the incident sunlight by hundreds of times due to the large surface area of reflectors. However, some require sun tracking as only direct sunlight is absorbed by the receiver. Tracking can be done in one or two axes, creating a more precise path and producing more power. They work best in clear and dry climates for high temperature applications. The range of temperature which solar collectors work at is shown in the diagram below. As we can see, non-concentrating collectors are used in low temperature applications under 100 degrees Celsius, for example, water or space heating purposes. Concentrating collectors work in medium to high temperature ranges, reaching up to 1500 degrees Celsius, and are generally used for electricity production. However, the working temperature of each solar collector is dependent on the application and the heat transfer fluid. That is to say, there are several parameters affecting the temperature of these solar collectors. Lastly, we look at the differences between concentrating and non-concentrating collectors. The advantage of concentrating collectors include a higher output temperature, which is used for the production of electricity. These temperatures allow for the heat transfer fluid in the solar thermal system to have a thermodynamic match with the turbines being used in solar thermal power plants. Also, the receivers in concentrating collectors allow for lower heat loss compared to absorber plates in FPCs or the heat pipes in ETCs. The cost is also reduced as there are less complex components, which mainly consist of mirrors. However, the disadvantage of concentrating collectors is that most cannot make use of the diffuse radiation as compared to non-concentrating collectors, which still absorbs the diffuse radiation. Also, most require tracking of the sun to maximize solar radiation captured. Finally, there's a need for maintenance to ensure the surfaces remain reflective. This concludes the section on the overview of solar thermal systems and the solar collectors. Next, I'll pass the time on to Alan. Thank you.